today I will focus a little bit on skin, and then we also know that those environment is not perfectly only good for the tissue regeneration. If you put it into the wrong microenvironment, the cell can also be damaged. So later part, we also have some study that if we give a wrong the environment, that what will happen during maybe, for example, like microenvironment transition or abnormal microenvironment. So by using the bioengineering approach, we like to start from the big macro scales. So what we can do is that we develop some novel skin flap chambers that originally we know that if we want to study the skin flap necrosis, we will just take a full thickness of the U-shaped skin flap and then suture it back and see how the skin will necrosis. However, there are several factors that will affect the outcome and cause the unpredictable, those uneven distribution of the necrosis. So what we did is that we create this kind of chambers, and actually it's a titanium material with several layers of the silicone rubbers that we can isolate the tissues that become an independent flap. So what we can do is that, for example, like this is a red dorsal skin, and we can create a full thickness skin flap here, and then the black dot indicate the cell we can inject before we have this kind of the skin flap. So we can have insist a full thickness and then assemble the chamber. At the bottom of the chamber, we have the medical grade silicone membrane so that we can isolate the interaction from this kind of the those vessel or other interaction of the cells. So and then put it back. So the flap circulation will naturally only apply from the vessel that at this connected area, and we can observe the necrosis very nicely. So, for example, we can use in this kind of flap to study how the skin necrosis in healthy or diabetes rate. And then we can also use this kind of flap. We could create a more challenging, more narrow flap to see originally even a healthy flap will necrotic, like only maybe 20% survive. However, if we can inject, for example, like a different kind of cell, like in here we showing this human umbilical vein endothelial cells, so we can prevent the necrosis. Besides that, we also create some systems that we can detect the skin traction during scar formation. So for example, this is the microchip we developed. So we can assemble, we create a wound on the dorsal of the rat, and then this is the Bluetooth chip that can simultaneously monitor how big the traction force is 24 hours. So during the wound healing, we can record the force, and then we can also apply the passive stretch to create a scar. We can know that how big the scar can form, and then during the scar formation, how's going on for those force change when we have the normal force. And then we're also interested about the stem cells, and then I know that Professor Yoshimura is the expert for the adipose stem cell, so I will quickly go through this part, and then we also learn a lot from his excellent work. So the reason we are interested in the adipose derived stem cell is because it is similar to the mesenchymal stem cell that can differentiate into bone, adipose, and cartilage. Beyond that, there's more advantages, easy accessibility, more abundant than bone marrow, and there's low compliance, autologous. So there are already a lot of the stem cell bank for the adipose derived stem cell out there. So when we we use the adipose derived stem cell, we create the first microenvironment we create is the chitosan microenvironment. So we nano deposit the chitosan on cell culture surface and use the helminth force microscope to see how the feature is. And indeed, we see it actually it's a very even surface. It's only within the 5 to 10 nanometer scale of those narrow small dot of the chitosan molecules. And the reason we like to put the chitosan on the cell culture surface is because it's biocompatible and biodegradable. We only like to see how the cell responds when we put it on. And surprisingly, what we found is this is monolayer culture of the stem cell. However, when we culture that chitosan coated dish, the ASC will spontaneously form a sphere like this kind of shape. Then when we take the confocal, we see that those sphere express neural lineage. So it's, in the center of the sphere is expressed the nestin and the neurofilar heavy chain, so it's like a mature neuron. However, on the peripheral of the sphere is expressed GFAP. So we call this a mixed population of the neural lineage cell for those sphere, and it can be used for the neurodegenerations. So we know that the chitosan has this kind of property that can help the cell to form sphere. And later on, we'd like to know what can we use it for hair. And then now we know that the hair also has a structure like dermal papilla is like sphere structures. And then the surrounding tissue has adipose stem cells. So what can we do by using this kind of those methods? So can we really create an artificial structure to induce the hair regenerations? So what we did is we take the red viversa dermal papilla cells, and then we can primarily culture it, and then we also culture those dermal papilla cells on chitosan coated dish, so they can spontaneously form the sphere after 3 days. So if it is regular cell culture dish, that will become a monolayer. And what we found is that after several passage, the primary culture of the dermal papilla cell will lose their dermal papilla characteristics. However, if we preserve, then in the 3D culture, that those vesican and hay1 can be preserved when we simply form the sphere for those dermal papilla cells. So those are the hay1 staining to indicate that indeed when we culture the sphere, they will maintain the dermal papilla characteristic. However, when we put those spheres into the new mice, we cannot regenerate the hair. So what we think next is that maybe we need more to assemble this kind of the hair spheres. So we know that the adipose tissue is next to the dermal papilla cells. So what we did is that we can either add the ASC into a mixed assembling, so that will become a adipose cell mixed with dermal papilla cells and become a whole sphere. Or we can use a sequential loading of those cells to create a cold shield assembly. So in here, we can let the dermal papilla form at the first day, so the core will be a dermal papilla cell. And then on the second day, we put the adipose derived stem cell, and then they will form this kind of the cold shield-like structure. If it is a mixed, then the green color and red color will mix together. So it's indicated, green color is indicated by the dermal papilla with the marker of vesican, and then the red color is the labeled adipose stem cells. So what we found is that we can use in this kind of sequential loading to make the cell look like a core as a dermal papilla cell. The shell is the second outer layer is adipose derived stem cells. And by that, we found that this kind of cold shell structure can further promote the vesican and the hay1 after we form this kind of cold shell structures. And we know that in our adipose tissue, actually it's not only contain the adipose derived stem cell, it also contains mature adipocytes. So what we would like to know is that if those two types of cells can promote, both of them can promote the hair regeneration, or maybe only one. So what we did is that we isolate the ASC, and then with the same batch, we are using a adipogenic medium to force them differentiate into mature adipocytes. So this is a red cell, so indicate that this is the ASC cell with a stem cell marker. When we differentiate them into a mature adipocyte, they will lose the stem cell marker and become the beta gamma expressed the mature adipocyte. This also happens in human cells, so it's indicated by the stem cell marker and the mature cell marker. Besides that, we also use the oil red O to see how the mature adipocyte will accumulate the oil droplet in the cell, but not in the adipose stem cells. So then we can use these two, we can separate 100%, like we have the adipose ASC, and then we have the mature adipocyte, to study how they will affect the cold shield. So, and what we found is that only the ASC, when you form a cold shield, it can promote the vesicant, but not the mature adipocyte. If we form the cold shield by the mature adipocyte, the vesicant will decrease. So, and this is also confirmed by using when we take out the conditional medium from the ASC, and then or from the mature adipocyte, and we found 100% of the ASC conditional medium can promote the ALP, the staining for those dermal papilla cells. So indicate there are some paracrine effects secreted from the ASC to promote the alkaline phosphatase activity in dermal papilla cells. Then we injected those all different kinds of like dermal papilla cell or the dermal papilla sphere, or like dermal papilla sphere with the suspending the ASC, or with this kind of the sphere, like with mixed sphere or kosher sphere. And into the we use patch assay to study the hair formation, and what we found is that the ALP staining will only occur when we have the cochlear structures in new mice. And then we also found this kind of the hair structures like using K5 or AE15 to stain the hair formation during the marker during the hair formation. And then we also looked into what happens when we inject those cochlear spheres. And what we found is that especially for those di-labeled adipose stem cells, after they injected into the subcutaneous, they will scatter out. And then, so the red color means that those are di-labeled ASC, and then they are co-expressed with the PIPA alpha. So the PIPA alpha, we think, is the major player that can promote the hair genesis, but not the gamma or delta. Delta may be a little bit, but still not sufficient. What we next did is that we also use the gain and loss of function by using the PIPA, different agonist and antagonist of those different PIPA isoform. So what we found is that when we added PIPA alpha agonist into the ASC and then let them form the sphere, we can further promote the hair. There's more hair formation. However, if we use the PIPA alpha antagonist to before we form a cochlear structure, then those cochlear sphere will not form the hair. So those are the published data. So then we'd like to know what can we improve. So we have some ongoing study. Like we learned some information from interviews, and then what we know is that this kind of the cartoon draw like adipose progenitor cells, that they are a little bit far away before the dermal papilla cells. So there may be also other cells that can interact. So what we like to have now is that maybe we can form different layer by layer structures. For example, we can have the core, again, maybe dermal papilla cell, but however, the second layer can be bulge or matrix cells, and then the outer layer can be eggs, the equal size. And the second thing we like to do is that we like to have a precise dermal papilla sphere. The reason we like to do that is because that what we found is that the dermal papilla sphere is uneven distribution, and we definitely, when we do the hair neogenesis, we definitely don't want a regenerated hair with a mixed size of the hair. For example, you can mix with the forearm hair with your regular hair, then that would be, or like the wrong size of the hair will grow in the wrong direction. So if we can precisely control the dermal papilla sphere, then we maybe can create different hair type. And then we are also using those artificial strategy to arrange different layers of the shell to see how they can do the molecular signal interactions. For example, like FGF, BMP, or wind signals. And in here, particularly draw our attention is that the FGF signal, because it's partially released from the deposit progenitor in naive microenvironment. So those are our other projects. What we found is that but it gives a very important cue to see that when the cell form the sphere, how they will change their cell signaling and surface profiling. So what we found is that the adipose, this is adipose stem cell, they form this kind of we call the neuron-like spheres. And then during the form the neuron-like sphere, what we probe their the FGF receptor, different FGF receptor from 1 to 4. And what we found from the gene and the protein expression is that the FGF receptor 2 and 4 will dramatically increase after they form the sphere. However, the FGF 3 will decrease when they form the spheres. So indicate that after they form the sphere, their ligand, they can receive different kind of ligand signals. So, and we know that during the the development or when we have those microenvironment, we have different FGFs. So we added the different FGF ligands and try to test what will happen. And this is again the ASC spheres. The interesting part is that originally we can form this kind of single big sphere. However, if we add a different type of the FGF, they will respond differently. For example, like here, what we found is that instead of forming a big one sphere, they will become several small spheres. And then we are still studying, and then the differential type of cell type also different. So, so indicate that when we have those sphere culture, the ligand can maybe respond totally different as compared to the regular monolayer cell culture. The second thing we like to do is this is the regular immunofluorescence staining. We have a very uneven cell culture, so the sphere will form a big one or a small one. And then if we collect all of them together, we can see this is hair one staining. The larger sphere will have a stronger hair one, the small sphere, the hair one will decrease. And can we use some this kind of semiconductor industry biotechnique to do that, to improve those things? So what we learned is that this is a study done by Professor Inter in Harvard. So they use this kind of the biomass technology to create artificial lung tissues. And we also use the same approach that we create this is what we call the kidney on a chip. So we create this kind of Bowman curve structure by using this is a microfabrication technique. So we can create this kind of structure within the very narrow co-culture systems. So with the biomass technology, what can we do for the sphere part is that we so we launch a project with the student called it a pachinko project. So and then so since we are in Japan, so if you don't know what's pachinko, maybe later on you can walk to the like Shijo or Sanjo, and maybe you can see some. The principle of pachinko is that we have some small stainless ball, and then we can magic. It's like magic is like a cell. So my student created this kind of feature. So we have all different like pachinko holes. So the pachinko holes, the bigger one that can contain, the more cell will falling down, so they will become bigger sphere. And the small one that will become small sphere. So we can decide if we want maybe eyeball hair, we can create a certain size of the hair spheres. And then well, can we do it? Yeah, indeed. So we can create all different sizes of the spheres. And then and of course we can use this for rapid screening. But now after we try those conditions, we can already, maybe later on we have the eyeball hair chip, we have the maybe regular hair chip. So in that case, we can create different kind of sphere and then use it for clinic. So with that, is all my presentation, and I'd like to take any question. Thank you.
So, is there any questions?
Thank you for the wonderful talk. I'm wondering, when you do the FGF to treat the sphere and change the size, is the induction ability alters after change the size, or they are all the same?
We didn't check it because so far what we found is that those are more, they are not the layer by layer sphere. So they are only, for example, the adipose stem cells sphere. And then what we found is that they differentiate into different types of cells first, but not the hair part.
Yeah.
So they become different neurons, particularly, for example, like strong cell neurons. And then we haven't tried that on the hair sphere, particularly cold hair, because what we thought is that after we assembled it, the signal, it will become just like a ligand for layer by layer passing through to induce the outer layer signal, and then let the cell maybe passing through. That will become like similar to what we did using the PIPA alpha agonist. And so now what we are doing is that maybe we can, after we define those key signals, we will gain of function or loss of function those cells. So, for example, we know those ligands, and then we can assign RNA the specific receptors, and then or that we can put more into those cells and then see how they will respond after they form the sphere. So that's our approach.
Yeah, I'm wondering, because you think that you have said dose depend on FGF to see the size change. I'm wondering, maybe the FGF dose will alter characteristic of the cells. They change the shape, or change they also the inside characteristics, those different size shape. They have different ability to do different things. That's I thought.
Yes, that's possible. So we have a different approach to do that. So we have two approaches, biomechanical part and also the engineering aspect, because the ligand can maybe change their surface tension or the cell type, so they will become smaller one. And then the second thing is what we already know nowadays is that the signal change. So that, for example, like the catenin signal is changed, so that they won't form a bigger sphere like as compared to others.
Thank you.
Josh? Yes.
It would be nice to know which FGF you're using.
That one is FGF9, but we tested several ones.
So when you put cells in a sphere,
Yes.
That doesn't mean they're all going to behave the same way,
Yes.
right? So have you looked at the variability between the spheres as far as the gene expression or any molecular markers? You make 100 spheres,
Yes.
and they're all different, right? Have you looked at that?
We try that if the major difficulty is what we found is that by using the immunofluorescence staining, what we now know is that they go to the same lineage, but just a different expression level because of the size. So for example, like Hay1, so they all retain the dermal papilla characteristic, but they just have the different protein expression profile because of size. And then if we use different like ASC, the sphere also has the same, they can go to the neural lineage, but the expression pattern may be the bigger one, they have a more mature neuron in the center. But they don't go to other lineage, so that's what we know now. And then so if we use a Western or we use the PCR, the signal are still the same, just because that the size will maybe cause the higher expression or lower expression, but the signal won't maybe one sphere goes to the cardiac differentiation, the other one goes to the control genesis. That won't happen in our cultural system yet. But we do indeed see the different the protein expression up and down for the same lineage. So we still can use for regular a big cell culture that indeed we have this kind of situation. So later on, for the dermal papilla part, we use a 96 whale, so we try to create a more uniform size. And then, but that's still not good enough, so that's why we have the biomass chip. So in biomass chip, we can really precisely control, like with maybe like a 10 or 20 micron interval for different, like a different size.
Okay, last question? No? Any questions? No? So do you have any time for the hair induction heat?
We hope to have it like, with around 200.
Micron.
Yeah, 200 micron.
Okay.
But some they will go bigger. Yeah, because bigger sphere like 300 and 400. The reason we don't like it to become over 300 or 400 micron is because sometimes they will have central necrosis.
Right.
So, but we know that the 200 micron sometimes also difficult to form hair. So it's kind of like it really depends on if it's very easy to form hair. Maybe the hair type is not the one you like.
Okay, thank you very much.
Thank you.